Hey y'all, in this video we're going to be talking about Taylor polynomials. What are they? Why do we have them? And then hopefully we'll be able to derive a few known Maclaurin series that'll be useful for BC calculus. First off, what's a Taylor polynomial? Taylor polynomial is just this idea that if we know the first four derivatives of some function or X number of derivatives, we can construct a polynomial with those same derivatives. So we might have some sort of function, f of x that looks like this. We might be able to construct a polynomial that maybe, behaves, has the same derivatives at a certain value and may behave very similarly and can be used to approximate it. And when we start talking about the Maclaurin series, we can use this idea of a Taylor polynomial and construct an infinite series that is exactly identical to another function. All right, let's get to it. So what we want to do is we want to construct a polynomial that has these derivatives. I'll give you a second to actually try to do that. You can pause the video if you want to try to do this on your own. All right, here's the answer. This would be the answer. This would be a polynomial that has these derivatives. Hopefully you can see if we plugged in 0 into all of this, you would get 1. If we take our first derivative, you're going to end up with 2x plus 3x. Oops, not 2x, sorry. 2. Let's try that again. 2 plus 3x plus 5x squared over 2 plus 7x to the third over 6. And then if we plugged in 0 into that, you'd get 2. That would be the first derivative. Your second derivative, if we took the derivative again, you're going to end up with 3 plus, and this would be 5x plus, that would be 7x squared over 2. And so you would get 3. And likewise, you can see the next derivative, you're going to end up with 5 plus 7x, and then the next derivative is going to end up being 7. And so what you realize is there's going to be a pattern here. If you look at these denominators right here, those are just factorials. This is just 2 factorial, 3 factorial, and 4 factorial. And they're really there to cancel out with your power rule. So like, for example, this fourth derivative, when you multiply in front by 4 and drop the power by 1, then you're going to multiply by 3 and drop the power by 1 to 2, and then multiply by 2 and drop the power to 1. You're really multiplying by 4 times 3 times 2 times 1, which is this 4 factorial. And so that's what it's canceling out with. And so it creates this nice formula here that if we know the first few derivatives of a function, we can find a polynomial that has those same derivatives if we just follow this formula. And hopefully you recognize that up here, that these derivatives, they appeared right here, 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 and here, right? And so you can see those values right there, and that's the same way this formula works. All right, so we want to take this formula for a Taylor polynomial, and we want to construct a polynomial for sine of x. And so we're going to find the first 5 derivatives of sine of x, and then we're going to use this Taylor polynomial formula over here. All right, so if we say y equals sine of x, we're going to find first derivative, cosine of x, second derivative, negative sine of x, third derivative, negative cosine of x, fourth derivative is going to be sine of x, and this thing repeats, right? So we have our fifth derivative would be the positive cosine of x. Now we're going to evaluate each of these at 0. So this is going to be, so our y of 0 is just going to be 0. Y prime of 0 is then going to be 1. Y double prime of 0 is 0. Our third derivative at 0 is going to be negative 1. Our fourth derivative at 0 would be 0, and then our fifth derivative at 0, it would be 1, and this pattern would repeat. And so if we were going to come up with the Taylor polynomial formula, we would end up getting this 5th degree Taylor polynomial is going to end up being 0 plus our first derivative, 1x, plus our second derivative, which is 0x squared over 2 factorial, plus our third derivative, which would be negative 1x cubed over 3 factorial. Fourth derivative is 0x to the fourth over 4 factorial. And then finally, our fifth derivative would be x to the fifth over 1x to the fifth over 5 factorial. And we can smooth this out a little bit and get this is going to be x minus x cubed over 3 factorial plus x to the fifth over 5 factorial. And since these things repeat, you can imagine the next few terms would be minus x to the 7th over 7 factorial plus x to the 9th over 9 factorial, so forth and so on. And we end up actually getting a series here from n equals 0 to infinity of, let's go, x to negative 1 to the n is an alternating series, x to the 2n plus 1 over 2n plus 1 factorial. And so this series, as you go from 0 to infinity, this will exactly equal sine of x. So this is the exact same thing, this function right here. And so we can do this with sine. We can do it with cosine. You could probably figure out cosine on your own after doing this one. You do it the exact same way. And we can also do it with e to the x. Another reason we love e to the x is because e to the x has very simple derivatives, right? Y prime is just e to the x, and you can just go all the way down to however many you want to do. If let's say we want to do the fourth derivative, it's going to be e to the x. So if we were just evaluating this at 0, it's going to have a value of 1 because e to the 0 is 1. And all of these, all the way down, are all going to be 1, right? Because they're all just e to the x. So constructing its what is this? We wanted a fourth degree Taylor polynomial. So our fourth degree Taylor polynomial for e to the x would just be 1 plus 1x plus 1x squared over 2 factorial plus 1x cubed over 3 factorial plus 1x to the fourth over 4 factorial. And you can imagine, we obviously don't need those ones, so we can go ahead and imagine this is going to be 1 plus x squared over 2 factorial plus x to the third over 3 factorial plus x to the fourth over 4 factorial. And if we wanted to get exactly the value of e to the x, we would continue this on forever and ever, and you can see the pattern here. And so if we wanted to write a series for e to the x, it would just be the series from n equals 0 to infinity of, x to the, x to the n over n factorial. And this would exactly generate e to the x. And so we can use these in lots of other manipulations and approximations to get various series that are, forms of e to the x. When you get into BC calculus, you're going to need to know these 3 Maclaurin series. You will be manipulating them in various ways and finding different things. Like, for example, you'll be plugging in numbers like 2 into maybe one of these series, be able to get an approximate value for sine of 2 or things like such. Okay? Hopefully you found that useful. Thank you. Bye.